Imagine you have a giant pile of handwritten digits, and you suspect that behind each scribbled image, there's a small set of hidden factors, things like slant, thickness, loopiness, that generated what you see. You'd love to recover those hidden factors, and you'd love to build a model that can dream up new digits by sampling from them. This is the classic setup of a directed probabilistic model with latent variables, and it's been a thorn in machine learning's side for decades because the math gets ugly fast. The 2013 paper by Kingma and Welling, Auto-Encoding Variational Bayes, cracked this problem open in a way that ended up reshaping generative modeling. Here's the core difficulty. You assume your data was generated by first sampling a latent code from some prior, then passing that code through a probabilistic decoder to produce the observation. To learn this model by maximum likelihood, you need to compute the marginal likelihood of each data point, which means integrating over all possible latent codes that could have produced it. For anything more complex than a linear Gaussian model, say, a decoder that's a neural network, that integral is intractable. The posterior over latent codes given an observation is equally intractable, which rules out the classical expectation maximization algorithm. Mean field variational inference, which approximates the posterior with a simpler factorized distribution, requires analytic expectations that also don't exist in closed form for neural network decoders. And Monte Carlo expectation maximization, which uses sampling per data point, is far too slow to scale to large datasets. People had tried workarounds. The wake-sleep algorithm from the 1990s trained a recognition network alongside the generative model, but it optimized two separate objectives that didn't correspond to any coherent bound on the likelihood. Other stochastic variational inference methods existed, but used a naive gradient estimator based on the score function, which has notoriously high variance. Think of trying to estimate the slope of a hill by measuring its height at random points scattered all over the landscape, rather than taking careful steps in a known direction. The paper's central trick is what's now called the reparameterization trick, and it's elegant. Suppose you want to compute the gradient of an expectation, where the expectation is taken with respect to a distribution whose parameters you're trying to optimize. The problem is that the randomness depends on the very parameters you want to differentiate with respect to. The reparameterization trick says, rewrite your random sample as a deterministic function of the parameters, plus some external noise drawn from a fixed distribution. For a Gaussian, instead of sampling z directly from a Gaussian with mean mu and standard deviation sigma, you sample epsilon from a standard normal and compute z as mu plus sigma times epsilon. Now the randomness lives in epsilon, which doesn't depend on your parameters, and you can backpropagate gradients straight through the deterministic function. The variance of this estimator is dramatically lower than the score function approach. Armed with this trick, the authors construct what they call the Stochastic Gradient Variational Bayes estimator. The objective they optimize is the variational lower bound on the log marginal likelihood, which decomposes into two terms. The first is the Kullback-Leibler divergence between the approximate posterior and the prior over latent codes. This acts as a regularizer, pulling the encoder's outputs toward the prior. The second is the expected log likelihood of the data under the decoder, given a code sampled from the encoder. This is essentially a reconstruction term. When both the prior and the approximate posterior are Gaussian, the KL term has a clean closed form, and only the reconstruction term needs Monte Carlo estimation. They found in practice that you only need one sample per data point, as long as your mini-batch is reasonably sized, around 100 examples. When you instantiate this framework with neural networks for both the encoder and decoder, you get what we now universally call the Variational Autoencoder, or VAE. The encoder takes an input, passes it through a neural net, and outputs the mean and variance of a Gaussian over latent codes. You sample a code using the reparameterization trick, pass it through the decoder neural net to get a distribution over reconstructed data, and compute the loss. Crucially, the whole pipeline is differentiable end-to-end, so you train it with ordinary stochastic gradient descent. The KL regularizer is what distinguishes this from a regular autoencoder. It prevents the encoder from just memorizing each data point with a unique code and forces the latent space to be smooth and structured, which is exactly what you need if you want to generate new samples by drawing from the prior. On experiments with MNIST and the Frey-Face dataset, AEVB converged faster and reached better variational lower bounds than wake-sleep across latent space sizes ranging from 2 to 200 dimensions. Strikingly, adding more latent dimensions didn't cause overfitting, because the KL term automatically regularizes unused dimensions toward the prior. When they estimated true marginal likelihoods using Markov chain Monte Carlo on low-dimensional models, AEVB matched or beat Monte Carlo expectation maximization while being far more scalable, since the latter requires expensive per-data-point sampling that doesn't extend to large datasets. Now, for the limitations. The reparameterization trick, as presented, only works for continuous latent variables, where you can express the sample as a smooth function of noise. Discrete latent variables don't fit naturally, which spurred a whole line of follow-up work on Gumbel softmax and related techniques. The Gaussian posterior approximation can be quite restrictive. Real posteriors are often multimodal or have complex dependencies, and the diagonal Gaussian can lead to blurry samples in image domains. The KL term can also cause what later researchers called posterior collapse, where the encoder ignores the input and just outputs the prior, especially when paired with very expressive decoders. And while the lower bound is tight, when the approximate posterior equals the true posterior, you have no easy way to know how loose it actually is during training. The forward-looking implications were enormous. This paper, alongside a contemporaneous independent paper by Rezenda Mohammed and Veerstra, kicked off the modern era of deep generative modeling. The reparameterization trick became a foundational tool that shows up in everything from Bayesian neural networks to normalizing flows to diffusion models. The idea of amortized inference, training a neural network to predict posterior parameters rather than running optimization per data point, is now standard practice. Now let's walk through some questions you might have after hearing all of this. First question: why exactly does the naive score function gradient estimator have such high variance compared to the reparameterization trick? The score function estimator works by treating the sampling distribution as a black box and weighting samples by the gradient of the log probability of those samples. Because the function you're averaging and the weighting term are uncorrelated in any structured way, you essentially get noisy estimates that bounce around. The reparameterization trick, instead, lets you push gradients through the actual computation graph that produced each sample. So each sample directly tells you how the output would change if you nudged the parameters. Much more informative per sample. Second question: what's actually preventing the variational autoencoder from collapsing into a regular autoencoder that just memorizes inputs? The KL divergence term in the objective penalizes the encoder for producing posteriors that are too far from the prior. If the encoder tried to encode each input as a sharp delta function at a unique location to enable perfect reconstruction, the KL term would punish it severely. So the model is forced to use overlapping, fuzzy posteriors that share latent space, which produces a smooth manifold where nearby codes decode to similar outputs. That smoothness is exactly what makes the model generative rather than just compressive. Third question: why does the model not overfit when you add tons of latent dimensions, which feels counterintuitive? Normally, adding capacity means more risk of memorization, but the KL term pushes each latent dimension toward the prior, unless using it actually improves reconstruction enough to justify the KL cost. Unused dimensions effectively get turned off, with the encoder outputting the prior for them. So the variational objective has automatic capacity control baked in. You only pay for the dimensions you actually use, which is a beautiful property that traditional autoencoders lack. For large-scale recommendation systems, the techniques in this paper map onto several concrete problems. User embeddings are a natural place to apply variational autoencoders. Instead of learning a point estimate of each user's preference vector, you can learn a posterior distribution over their interests, which gives you principled uncertainty estimates for exploration and cold start scenarios. The amortized inference idea is especially powerful here because you can't afford to run iterative inference per user at serving time. An encoder network that maps a user's recent interaction history to latent code parameters in a single forward pass fits perfectly into a real-time serving stack. VAE-style models have actually been deployed for collaborative filtering, where the decoder reconstructs a user's full interaction vector from a compressed latent code, often outperforming matrix factorization baselines. Beyond user modeling, the reparameterization trick itself shows up wherever you need to backpropagate through sampling. For instance, in stochastic ranking policies, where you want to learn a distribution over candidate orderings, or in generative retrieval models that produce candidate items by sampling. And the KL regularization insight that you can prevent overfitting in high-dimensional latent spaces by anchoring to a prior is broadly useful when you're training large embedding tables that would otherwise memorize idiosyncratic patterns from tail users and items.